All right. Welcome back to Paleo Talks, everybody. You may have discovered that we're on a every other week schedule now and on episode 51. How you doing, Ethan? Welcome to the show.
Oh, long time listener, first time caller.
Ethan goes way back with us. He was actually a governor's school student, so State of Tennessee Governor's School. And well, you can tell us more of your history, but yeah, he's been a part of our fossil site actually since he was a high school student. Fantastic. And hey, Chris, how are you doing today?
I'm good. Tuning in from the Valley Brook campus of ETSU.
All right. And you were up in Saltville, Virginia yesterday, trouncing through the Pleistocene.
Yeah, Saltville still exists. We got ostracods galore.
Very good. Well, we won't be doing excavations up there, but we do hope to be back excavating there again next year. And we'll go over to David now before we introduce Ethan more fully. And tell us more about the show and how it works again, David.
Sure thing. Like Blaine said, we are on episode 51. So if you are a regular viewer, this is a familiar format now. We're going to introduce our guest here in a second, and then we're going to let Ethan go into his presentation all about lemurs today. And once the presentation is done, the remainder of Paleo Talks programs is Q&A. And so our panel of people here might have some questions, but we especially want questions from the audience. So when the presentation wraps up, go ahead and drop your questions in the comments of the Facebook video. And as always, if for any reason you can't leave a comment on Facebook, you can find us at the Gray Fossil Site Twitter or Instagram account and send us a message there.
All right. Thank you, David. I guess one thing we have to start off with right off the bat here is happy birthday to Ethan.
Birthday.
Happy birthday. So first time caller and first time birthday on Paleo Talks as a guest. So that is fantastic.
That's true.
So we want everybody to sing starting right now. Go ahead, David.
Yeah, we will. I was going to say everyone in Maryland and Amsterdam and Badlands.
Yeah, in whatever language. Right. So yeah, as I mentioned, Ethan has been with us for a long time, and it's just been wonderful to see him jump through all of the hoops of different education and different institutions, and now has his PhD and has a full-time job doing paleontology. And so let's jump over to you, Ethan, and you can give us your story and your perspective on that trail of paleontology and how you got into it in the first place, and maybe even how the Gray Fossil Site had a little bit of a role in that.
Sure. So I'll get so is my presentation showing?
Not right now. It says it was deleted, I think.
Oh no.
Oh.
I'll reshare here. There we go.
There we go.
All right. Yeah, so here's, as we usually do on these things, or you all do a little background about how I came to paleontology. So I'm from East Tennessee. I'm from the Knoxville area. In high school, I guess I kind of got interested in human evolution. So that was really my angle of interest in paleontology. I actually read, if anyone's ever read Desmond Morris' The Naked Ape, it's a terrible book, but it's a very interesting book.
It was quite a hook for me too, even though you learn about how wrong it is.
Right. So I kind of expanded out from human evolution to get a little more interested in primates, and then a little more interested in mammals more generally. And actually, it was really in high school, I kind of thought, oh, I want to be a primate paleontologist, and I really like the Eocene, which is actually what my dissertation was focused on. So that's an unusual amount of continuity, I think, for a very specific topic. But my dissertation ended up not being on Eocene primates, it was on lemurs, but I did collect data for Eocene primates that I'm working on now. But while in high school, I did attend the Tennessee Governor's School, which was very formative for me in a lot of ways, because it's this Tennessee Governor's School for the Scientific Exploration of Tennessee Heritage, where we did, we had a Tennessee history class, which I loved, and an archaeology class, and then learned about old-time music, which for the first time, which I'm an old-time fiddler now. So, and then also we went to the Gray Fossil Site, and this is not, unfortunately, a picture from that governor's school. I remember taking pictures, but I guess they all got deleted. But I did find a tapervert in that governor's school. So that was my first.
You know,
one.
Ethan, that's not a very good picture. I can't tell what I'm looking at.
So this is from, so I came back when I went to college at UT, so you see the logo there. I did anthropology and college English anthropology, but I've worked summers at Great Fossil Sites. This is my first summer at Great Fossil Site, the first fossil I found in my first summer, and it's an alligator vert. See if I can get a pen, so it's that. I think I broke it probably when I was digging, and I broke off that little. But that's my great connection. Yeah, and I worked several summers there, and did a research project with Dr. Wallace there on panda dimorphism, and you know, it was never Paleogene mammals, which are, you know, my deepest, truest love, but it was very exciting and a cool place to work. And I'm currently a faculty member at a medical school in Kentucky, but I'm moving to another one in East Tennessee, and I hope to continue to work there at the Great Fossil Site. So yeah, so to complete the story, I went to Duke University. I did a PhD in evolutionary anthropology there, and you'll see my dissertation because that's basically what this talks about.
Yeah, so see, David, he's actually moving much closer. He's going to be down in Knoxville.
Yeah, you can't escape. We're bringing you back slowly, town by town.
So quickly, Ethan, what did you discover about our red pandas at the Great Fossil Site?
So at the time, there were 2 skeletons that had been found, and one of them seemed to be much larger than the other. And so what I did was just basically a bootstrapping kind of approach, where I sampled a bunch of the modern red panda, and I took 2 individuals, or basically drew from the population of moderns that are in museums, two pairs of individuals, and saw how likely it was that the 2 fossil skeletons are as different as they are if they were drawn from the same population distribution as the modern red panda. And what's significant about that is the modern red panda is monomorphic in size. They're all about the same size, males and females, whereas these seem to be quite different in size. So, you know, you can't really know, maybe they were just biodistribution, but as far as that statistical approach can tell you anything, it suggests that these may be sexually dimorphic, which is unusual for, you know, a red panda.
Cool.
So that's fun.
Now, that paper ended up being published in PE, so I can actually drop a link to that in the Facebook comments if anyone's interested in looking more into that research.
Thank you, David.
Yeah, and well, and I guess one last career note. So right now I teach anatomy. So I teach gross anatomy to medical students, and I would just plug that as a career path for paleontologists. If you're out there and you're looking.
Yeah, we were actually. I mean, you were up here yesterday doing research with us, and we talked a little bit about that because it really is an avenue that a lot of people don't think about, is teaching anatomy as a paleontologist, teaching human anatomy as a paleontologist. And there's a growing number of paleontologists that are doing that. And so thanks for bringing that up. All right, we'll move right into your research that you're going to talk about today. And just to remind everybody again, coming to you from East Tennessee State University and the Center of Excellence in Paleontology. Take it away, Ethan.
Yeah. So this talk's going to be about lemurs and sort of framed around the question of whether or not lemurs represent adaptive radiation. I may or may not answer that question, but we're going to frame around that question. So lemurs are a kind of strepsirrhine primate. There's 2 major groups of primates, strepsirrhines and haplorhines. You and I and apes and monkeys and tarsiers are all haplorhine primates. And then lemurs, a group of animals called bush babies, the galligos, and lorises, which you may know from the internet. They're the things that do little arms when you tickle them. You shouldn't do that. That's their like fear response, and you're really stressing them out. It's terrible. But that's what that animal is. It's a loris. Those are all the strepsirrhine primates, and this is where they live. Galligos live in tropical Africa. Lorises are actually distributed both in Africa and in Southeast Asia, but lemurs are totally restricted to this island of Madagascar, which is an interesting sort of biogeographic puzzle. How'd they get there, and why are they only there? So the first crown strepsirrhine, the first strepsirrhine that's definitely within the modern radiation, is that there's a couple of them from the Eocene of Egypt, Watalemur carinizia, and we know they're members of the modern group. Move my little window here. Because they have this unusual modification of their canine. See how the canine is kind of long and pokes forward? That's called a procumbent canine, and it's part of a structure called the tooth comb. So all strepsirrhine primates share this modification of their anterior dentition that they, oh, that's, sorry, I don't remember how to erase, that they use to groom themselves. And it seems to also be part of their scent gland distribution. So the lemurs have these scent glands distributed on their body, and they can kind of get a little bit of the scent and then distribute around their fur. And they also just groom their fur with it. Some of them use it to feed, but it doesn't seem to have evolved from that. It seems to evolve for this grooming function. But that's actually the canine there. And this is actually a premolar. It's modified. So when you see that, you know you got a strepsirrhine. But the earliest probably close relatives to strepsirrhines are also from North Africa, these Lemurids. And then strepsirrhines are probably related to, or rather, this fossil group Adaptations is probably also strepsirrhine, but it's not a crown strepsirrhine. So the point is that strepsirrhines seem to evolve, or crown strepsirrhines at least, in Africa. And their original fossils are in North Africa, because in the Eocene, North Africa was much wetter and milder. And as climates cooled and dried, they've gone down into tropical Africa and tropical Asia. So this leaves the question, how do they get to Madagascar? How do these lemurs get to Madagascar? So what are lemurs? So lemurs are actually about a quarter of all primate species. They're really diverse radiation. They occupy pretty much the full range of primate diets, locomotor modes, social systems on the less complex level. None of them are as complex as chimps or something like that. They're not smart, but a wide range of social systems beyond that. And some of them have things that aren't seen in other primates, like female-dominated social systems. And then they're active, the full range of primate activity patterns, day, night, ephemerality, all that sort of thing. So we'll walk through just the families here. So we have Andreids. Andreids are mostly folivorous, and a lot of them have this vertical clinging and leaping locomotor mode. This is a woolly lemur. And Andreids also include these things called sloth lemurs, I'll talk about later. We have Archaeolemurids. This is an extinct family that are sometimes called the monkey lemurs, because they seem to have been terrestrial. Lemurids, I think of these as kind of just your basic lemur. They're very, they look a little bit dog-like, and body proportions are all pretty arboreal. They eat fruit mostly, a little bit of leaves. Cargaliids, which I had to include 2 cargaliids because they're my favorite. Dwarf lemurs, like these guys, and then mouse lemurs. These are the small ones. Dwarf lemurs are really distinctive because they hibernate, and they have, some of them, the fat-tailed dwarf lemurs, actually store fat for their hibernation in their tails. So their tails get really fat, and then they work through it in the winter. And then the sportive lemurs, called the Lepidlemurids. These are also vertical clinging and leaping lemurs. Have really unusual teeth. They're just unusual. And they're a huge group. They're actually the biggest genus of lemurs. And then Megalodaphids, oh, there's a picture. These are the koala lemurs. That's an extinct family. These are some of the largest lemurs. And then finally, the Daubentoniids, the ii. And then it's possible fossil relatives from the mainland of Africa that I'll talk about in a minute that are in this group, Cariformes. So ii is the most unusual lemur. They have this long middle finger that they use to tap on wood to find grubs, and they can kind of spear the grubs. They also have these highly developed incisors that they can gnaw through wood, and they can also gnaw through fruit. They have this unusual diet of grubs and the insides of hard fruits. Really strange. A lot of people analogize them to woodpeckers. They seem to fill the woodpecker niche on Madagascar. There are no native woodpeckers in Madagascar.
So even the large ones that went extinct, that was relatively recently in time, wasn't it, geologically?
Right. So those went extinct probably after human contact, almost certainly.
Just a few thousand years ago, or more than that?
I think the oldest, trying to think about the earliest, it's uncertain when something went extinct, right? But we have subfossil lemurs from a few thousand years ago, so into the very latest Pleistocene. And then we know we have historical records from French and from Portuguese explorers of seeing things that were probably these things into the, at least into the 14th century.
And just give us an idea of, what is the largest lemur from the past?
So I think I have a slide for that.
Okay, cool.
But first, here's some actual pictures of these things. They all happen to have babies, but that's just a coincidence. So we have, so this is Lemur cata. This is probably your most famous lemur. It's a lemurid. When you think of a lemur, you usually think of Lemur cata. So ringtail. This is a shafak. So the shafaks are these highly specialized vertical clinging and leaping lemurs that when they're on land have to sort of bound around bipedally. Zabumafu, if you remember Zabumafu, that was a shafak. That was a shafak actually. These are all pictures from the Duke Lemur Center.
That was my most important question actually, was which one is Zabumafu? So
Yes. Yes,
my
we'll
daughter
talk about
watched that
shafak.
show. Okay.
Yeah.
That had a ringtail though, didn't it? I don't remember.
I don't know if
Maybe
there are
not.
other lemurs.
Well.
If you had lemur friends. Yeah, Shafak was actually the actor, if you want to call it that, who played Zabumafu. Was a Shafak named Jovian who lived at the Lemur Center until 2014, 2015. He died, but his actually this little lemur guy, that's his grandson. So there's still that lineage is still around. And this is a mongoose lemur here. So mongoose lemurs are also lemurids. Yeah, so these extinct lemurs, focus on those a little bit because this is a paleo talk. So there's some extinct, totally extinct families. So I mentioned already the monkey lemurs. So Archaeolemur and Hadropithecus. There are these lemurs called sloth lemurs, the Paleopropythecids. Now, genetic evidence suggests that they actually nest within Andreidae, so they're not really a family anymore, but they're distinctive. Because they all have this below branch quadrupedalism, like a sloth. There's no other primate that does that now. And then Megaladapus, the koala lemur. And then back here, I actually don't, because there's no M2 for this, so it doesn't exist as far as I'm concerned, as I study lower molars. But this is actually the largest lemur, the Archaeoindris. So Archaeoindris is about the size of a female gorilla at largest. So they really hit the full size range for primates. And then Pachylemur here. Pachylemur is really just a bigger version of this lemur called Varicea, which is a modern lemur. So less exotic, but kind of cool. Yeah, and as we were talking about, these all went extinct either shortly before or after humans came to Madagascar. So humans, this is a debate, whether or not humans played a role in the extinction of these lemurs or whether or not broader environmental changes, the end of the Pleistocene and other kind of shifts in forest habitats on Madagascar were primarily responsible. It's similar to the conflict, debates people have in North America, debates people have in Australia about extinctions. Could be both. This is a hippo. There's actually extinct hippos on Madagascar too, which are sort of interesting. Anyway. Oh, and this is a weird animal called Biddy Malagazia. I shouldn't have attempted to say that because I can't remember exactly what the animal's called, but it's a really unusual Malagasy animal. Anyway, okay, back to lemurs. So how do they get there? So we know that strepsirrhines evolve on mainland Africa, most certainly. And Madagascar has been separated from Africa at least since the Jurassic. So this cannot possibly be a vicarious thing. There were not lemurs running around in the Middle Jurassic. So there's two major ideas. The first is a sweepstakes dispersal. So this is a rare event where an animal gets caught on a raft of vegetation, is usually what people think about, and washed out to sea and crosses some ocean body and gets to somewhere. So this is how a lot of islands are thought to be colonized. The most famous and most extraordinary and most apparently, there's no other alternative to it, version of this is how monkeys and rodents get to South America. So apparently monkeys cross the Atlantic Ocean. I mean, there's no other way to get them there really. So this is another somewhat low chance, but apparently it may have happened, a dispersal across about 400 kilometers of open ocean from Africa to Madagascar. This is the dominant idea for how lemurs got to Madagascar. This is actually from G.G. Simpson, and he's using this as an example of how you can detect a sweepstakes dispersal. And his argument here is that we think it's a dispersal because of the unbalanced fauna. So you have on mainland Africa, you have a lot of animals that just never get to Madagascar. And so why not? Well, if you're an elephant, you probably can't go on a floating raft of vegetation. If you're a lion, an antelope. There's some other animals that could have gotten there. There's no reason that a small cat couldn't have dispersed, but they just didn't, just for bad luck. That's the disappointed ticket holders. That's that idea. And then these are the animals that just happen to win the lottery and get to Madagascar. And then these are the times when they may have gotten there. So this is a pretty old idea. It's the dominant idea. If you go to the Duke Lemur Center and do the tour, that's what they'll tell you happened. Maybe. And then the other big idea, which has always kind of been around, is this idea of land bridges. That there may have been some lost physical connection between the Mozambique coast and Madagascar. Land bridges always sound a little bit archaic, like this is what people used to think before plate tectonics. There must have been these giant land bridges connecting the continents. But there is a feature in the Mozambique Strait called the Davy Ridge that runs in the direction you would need it to run. So you can see it here, and to connect the two land masses. It's basically a ridge with some seamounts, has some volcanic activity. And these authors, as the masters, this is a brand new paper. I wish I had cited it in my paper, but it came out a little bit too close together. But they make the argument that, I don't know, it's actually a little bit compelling to me, that this Davy Ridge could have been exposed subaerially, at least in 3 intervals, where there's some evidence from the carbonates. There are 2 lines of evidence. The carbonate deposits that show some evidence of sort of karst topography forming, which presumably would only happen if it's above the water and is being rained on, and the carbonates are being eroded or dissolved rather. And also from ashes that only could have deposited subaerially or in shallow water. So from those bits of evidence, they argue that this ridge, or these parts of it, were above water for at least 3 intervals. So the Paleocene interval, which is actually when they say lemurs may have dispersed, that's too early. So that has to be wrong. But a Oligocene interval, which is interesting. So put a pin in that, put a pin in the Oligocene. And then a Miocene interval. And they explain the dispersal of these animals that Simpson says came over on rafts as dispersing in pulses during these exposures. I should have said when I was talking about extinct lemurs that my plan was to say the reason this is also hard to disentangle is that Madagascar has no fossil record between the Cretaceous and the Pleistocene, essentially, or really the late Pleistocene. All of that rock, either it never formed or it was eroded away. So there's no good terrestrial deposits on Madagascar that have been found, and fossils have been found in so far. There's some suggestions that maybe they might have some on an island off the coast, which is very exciting. So maybe we'll get fossils from the Paleogene Madagascar. But for now, we're having to do all of this without any fossil record.
Do they think that was island hopping or a continuous bridge?
They're open to both possibilities, I guess. And island hopping would explain maybe some of the filter that you see, the unbalanced faunas. It's interesting. I think the strongest argument they make for at least that Miocene bridge is the hippos, because you would think, oh, hippos can swim, and that's always been the idea that hippos not going to go on a floating raft at vegetation, but maybe they can swim. But modern hippos really can't swim. They're actually really bad swimmers, apparently. They just kind of walk on the bottom, and they can't survive open ocean really. So that's actually the hardest thing to get there is the hippos.
And in contrast, elephants do swim. So probably aliens. Probably aliens.
Although maybe Miocene hippos were different, right? So we're making a uniformitarian assumption there, I guess. But interesting, crocodiles. People think maybe humans introduced the crocodiles for some reason. I don't know why you do that, but anyway. So another complication to the traditional story of how lemurs get to Madagascar comes from some new fossil descriptions. So traditionally, people have thought lemurs get to Madagascar in one dispersal, almost certainly in the Eocene, at least the Middle Eocene, at the very latest Middle Eocene. This comes from molecular clock dating of the last common ancestor of all of the lemurs. So that's the ii and then all the rest of the lemurs, because you remember that tree, the ii is the outgroup of the rest of the lemurs. This study by this guy, Greg Gunnell and colleagues, make an interesting suggestion. It's basically that 2 very strange enigmatic fossils from the mainland of Africa may in fact be relatives of the ii. So the first is this thing called Plesiopithecus that's from the Eocene of Egypt. And the second is this thing called Propado, which has a very complicated history because it was first described as a loris by Alan Walker, and then not by Alan Walker, by G.G. Simpson. And then Alan Walker said, no, it's a bat. But then Greg Gunnell, who happened to be this world expert both in bats and in early primates, was in Kenya and looked at it and was in the unusual position to say that's not a bat, and it really looks rather like Plesiopithecis and rather like something you would expect to evolve into an ii. And so they did a phylogenetic analysis. They actually didn't even include the most obvious similarity, which is this procumbent first incisor. So this is Plesiopithecis and this is the ii. So even excluding that, details of the dental characters, root morphology, and then some geometric morphometric approaches all support this link. It's controversial, definitely not accepted by everyone, but if it's true, it does some interesting things. It suggests there must have been two dispersals. So there must have been the dispersal of the most of the lemurs, and then a dispersal of these ii relatives. And it actually decouples the dispersal from that date, that early Eocene date, because now you're dating from the differentiation of all the rest of the lemurs, which happens really in the Oligocene. So Oligocene keeps coming up. So there's one more bit of sort of background about Madagascar. So after Madagascar splits from, well, first Madagascar and India split from Africa, and then Madagascar splits from India. So Madagascar kind of does this doop doop. So once it is free, it moves through, as it moves north, the global aridity belt. So these are formed by Hadley cell circulation, and it's where you have deserts all around the world today, sort of above and below 30 degrees latitude. As it moves through this aridity belt, it's thought that this is what scrubs Madagascar of all of its Mesozoic fauna, because Madagascar does have a Mesozoic fossil record and it has weird animals, weird mammals, as dinosaurs. Obviously, dinosaurs go extinct everywhere, but these things, they really don't have any residuals in the modern fauna. They just all go extinct. And maybe they just go extinct over time, but the idea is maybe they go extinct when Madagascar moves to this desert belt and all the climates change on these animals and they can't cope. Well, it only moves out of that zone in the Oligocene. So this about 30 million year time frame is when you're beginning to see, so here's the aridity belt, maybe something like that. When you're beginning to see it move kind of decisively away from the influence of those drier climates. And this may be a period of forest spread on Madagascar. This is an idea from this geologist Wells, and maybe creating kind of the modern Malagasy environments that lemurs might be evolving to exploit. All right. So to this concept of adaptive radiation. So the initial dispersal of lemurs to Madagascar is often thought of as a classic example of a true adaptive radiation. Basically, lemurs get to the island, they see a bunch of open niches, and they just start going. Some of them become injuries, some of them become little mouse lemurs. They occupy all of these vacant spaces for primates. So this is I got a quote here from Simpson from Major Features of Evolution. More or less simultaneous divergence of numerous lines, all from much the same ancestral adaptive type and to different, also diverging adaptive zones. So a single lemur type is more or less simultaneously diverging into all of these different lemur ecologies that we see today. Yeah, so I just said. So the question I have is, could there be something else going on in Madagascar in the evolution of forests or other things on the island that are creating ecological opportunity for lemurs at intervals other than this initial dispersal that are really spurring lemur diversification, which would make it a radiation certainly, and would give, it obviously has adaptations, but maybe not this classic adaptive radiation model. And I chose to look at that in terms of dietary ecology. So diet is a very important aspect of mammal ecology. Mammals are very differentiated in their diets, and they have dental morphology that adapts them to eating foods of different types. And when you're talking about strepsirrhines, you're primarily talking about three broad dietary ecologies: folivory, see here, some kind of faunivory, mainly focused on insects, spiders, slugs, whatever, and then frugivory, which is almost the default for lemurs. And then one tiny complication is that a lot of lemurs and strepsirrhines eat gums, which we tend to include in the frugivory category, even though gums aren't, as far as a plant is concerned, a gum isn't like a fruit, but in terms of material properties, they're sort of similar. So the tooth of a gummivore looks like the tooth of a frugivore. And you can expect kind of predictable patterns of dental morphology in animals that are evolved to eat these different kinds of foods. So a folivore is going to have to deal with something that's tough, something that's flat and very planar, and really needs to be sliced up with blades, like that. Insectivore is going to deal with something that's also tough, but is also stiff. And stiff things have to be basically they have to have fractures driven through them elastically. And so what you're really going to want there is a projecting cusp that's going to penetrate that stiff thing, and then with its Young's modulus, and make it propagate cracks like that. And then very short blades. And then frugivores are going to eat things that actually want to be eaten in a sense. They're evolved to be eaten by something, but might have some hard seeds. So you don't want something that's going to be liable to fracture, like a nice pointy cusp. And so you're likely to have these kind of blunt, rounded cusps. And we can quantify these aspects of tooth shape using a suite of tools called dental topography metrics. So these are developed to be used on meshes. Let me get a picture there. So these meshes are generated by scans of teeth. You can get them in different modalities. And then you can calculate aspects of tooth shape from the scan, or from the mesh generated by the scan. One of the first was relief index. And relief index is really how much of the tooth projects into space. So the area of the tooth here in 3 dimensions divided by its footprint. So basically how pokey is the tooth into space, how much enamel is available to process things. There's also this idea orientation patch count. Orientation patch count is a measure of the complexity of the tooth surface. Basically, if you imagine a tooth as like a landscape, and it has hills that have an aspect, like a hillside has an aspect that you're going to point in a certain direction, you can see how many patches of different aspects there are on a tooth and count them up. And then that's your orientation patch count. And really what it's counting are these changes in aspect, and these are going to be sort of points where the tooth can meet a food item. And so it indicates its complexity. And then finally, my favorite personally, I'm biased, Dirichlet normal energy. Dirichlet normal energy takes advantage of the fact that a mesh is going to be made of little triangles. So we're like in, if any of the audience has read Timaeus, that's Plato's idea of how reality is made up of little triangles. So Plato was right, at least as far as dental topography metrics are concerned. So all these meshes are made of little triangles, and the triangles have an orientation with respect to each other, and you can get the second derivative of that. So the rate of change in the orientation of the triangles, and that's a measure of the bending energy, or the Dirichlet energy of the tooth surface. So a highly bendy surface is going to be a surface with a lot of crests, but also a lot of basins, that's going to give points for the tooths to process foods. So you would expect a folivore and insectivore to have a higher D&E. And you can look at the sum of that, and you can look at the variability of that. And the sum seems to capture a lot of the pokiness of a tooth, so really finds insectivores. And the variability really gets at how different a crest is from a basin, because in a folivore, basins tend to be kind of flat, and that tells you a lot about folivores. So these are cool tools, and they're all implemented from scans of some kind of lower molar surfaces. So the sample here is a sample of 170 of these second lower molars. I got every genus, but this one genus called Alocebus, the hairy dwarf lemur, that's very rare, really doesn't exist in any museum collections. These are micro CT scans. So micro CT is basically like medical CT, it's just high resolution. And then I did the dental topography metrics. So this is a discriminant function analysis. This is one thing you can do with these metrics. So if you combine all 3 metrics into predictive equations, basically predictive discriminant functions, then you can classify your extant sample, and you can also use it to classify fossils. So here we've got folivores, insectivores, and frugivores. And these are our subfossil lemurs, so those recently extinct lemurs. And I was able to classify them. So that's kind of interesting. And it shows that these metrics definitely do capture some aspect of dietary ecology in lemurs, or in strepsirrhines. These are all strepsirrhines. But to get at this question of adaptive radiation, I took some macroevolutionary modeling approaches. So all of these approaches are really focused around distinguishing two kinds of tree shapes. Your tree can look like this. So here, these are tip taxa. So that's a little lemur, draw a lemur. Okay, I can't do that 4 times, but there's another one, etc. And this is some metric upon which they differ. So this is kind of shape difference or something like that. So all of your difference can get partitioned early on, like immediately when the clade is formed. And that's something like what adaptive radiation does. Or your difference, the difference amongst the tip states can get differentiated later on in the tree. So here, there wasn't that much evolution in the initial cladogenesis, but there was quite a bit later on. And those are two tree shapes that you can use modeling approaches to try to distinguish. The first is this idea called a disparity through time analysis, and it's a little complicated to explain exactly what it does, but it's basically taking time steps through a phylogeny, and it's seeing how what percentage of the total morphological diversity, which we call disparity, is present at each time slice, and then comparing it to a Brownian motion model of a null model to see if it's significantly different than would just be random. And what happens in lemurs is that it's not significantly different from what would just be random. But you do have an interesting spike. So what this dark line shows is the empirical disparity present at each time slice as a percentage of the total disparity of the clade. And what you can see is there's a little bump in how much of the disparity accumulates right here. That happens to be the early Oligocene. That's interesting. Put a pin in it. The other approach you can take is a model fitting approach. So this basically looks at different ways that a trait can change along a tree. It could be, again, kind of a random walk, this Brownian motion. It could evolve towards a single optimum. That's this SSP, or it's also called Martin-Uhlenbeck. Or it could differentiate early by having a high rate of evolution early on and a slower rate of evolution later on, which is this EV model. And in lemurs, everything comes out Brownian motion, basically. One thing comes out SSP, but nothing comes out early burst. So that's that way of looking at the question. Another approach I took, and this is my innovation, so therefore perhaps much more dangerous, is I tried to reconstruct the ancestral ecology at each internal node, not by just reconstructing the categorical state, but by actually reconstructing the measurements for these dental topography metrics. So I reconstructed those back into time. I recombined them at internal nodes, and I did a distributional analysis to account for uncertainty. And I classified the internal nodes to a dietary ecology. Then what I was interested in, so that's what this is. So the green here are frugivory, and then the yellow is frugivory, and there's a little bit of blue in some places. That's insectivory. Most lemurs aren't really insectivorous, so it doesn't come out much. What I did was look at the transition towards frugivory, because that's the non-ancestral state. And here's what you find. You find a big pulse toward transitions towards frugivory, right, at the early Oligocene. So lemurs as a group a lot of them are evolving more frugivorous adaptations, apparently, in this early Oligocene interval. And then finally, one last approach was to look at the ancestral teeth shapes themselves. So we don't have fossils for any of these things, but what we can do is look at the modern taxa, and we can look at fossils that are outside of the lemur group, like these animals, Jebel lemur and so forth. And we can create, using Brownian motion evolution, we can create ancestral shapes, basically, that reflect the possible morphology of the teeth of the ancestors of the modern clades. And this work was really done by my collaborator, Shan, who's a mathematician at Duke. Or no longer Duke, she's at Mount Holyoke, but she was a PhD student when I was a PhD student. So her dissertation was also this, but just the math side of it. And what makes her approach so unique is that instead of you can do this right now with landmarks, basically, like you put some landmarks on a skull, you can warp a mesh back in time and get a new skull. This doesn't use landmarks. It actually uses the continuous shapes and then warps them back in a way that weights them for their the tree length and their closest relatives. That's useful because it means that when you do landmarks, you tend to get like weird holes in your shapes and stuff. So these meshes can be treated like the meshes that we get for the extant animals, basically. All right, so I'm almost done. I'm going late. Sorry. But basically, pulling these pieces of evidence together, I was able to propose a new model for lemur evolution. It's a little more complicated than just the simple adaptive radiation at the point of dispersal model. All right. So basically, we start from our ancestral tooth shape here. And this ancestral tooth shape really looks a heck of a lot like a loris or a gallico. And it also looks a heck of a lot like modern chirogaliids, or at least the ancestral chirogaliid. So these are animals that are probably eating a lot of soft fruits, insects, and gums, much like modern chirogaliids. So that's kind of the ancestral lemur morphotype. And if you imagine lemurs getting to Madagascar in the Eocene, maybe that's what these guys were doing for millions of years. They were just running around being mouse lemurs, basically, in chirogaliids. The big event in increasing lemur ecospace occupation is really this evolution in the ancestor of Endreids and Lemurids, so the large-bodied lemurs, where they evolve a tooth that's much more bilophodont. And by bilophodont, we mean it has two kind of parallel crests. And this isn't completely there, but it really approaches the bilophodont condition you see in more advanced Endreids. And that's interesting because you would think that ancestor would look more like a Lemurid, but it really looks a little bit more like an Endreid. And Endreids eat a lot of seeds, they eat a lot of leaves, and they eat a lot of defended fruits. So what I think is important here is that lemurs are evolving to exploit defended food resources, so things that plants don't want the lemurs to eat. So fruits that are still in the rinds, leaves, things like that. And then from there, you get a couple of different directions. So the ancestral Lemurid actually looks a lot like Lemur cata, who eats mostly leaves and then defended fruits. And then from there, you can get the adaptations for more fruit specialists, soft fruit specialists, like the lemurs and Varicea, or bamboo lemurs, which are a weird kind of lemur that eats bamboo. So that's this direction. And then on the other end, the Endreids, the ancestral Endreid tooth looks mostly like Propithecus. Propithecus is the most generalist Endreid. They eat a lot of leaves, but they also eat seeds. So if you're a plant, you don't want a Propithecus eating your fruits because it's really going to eat up all your seeds. And then from that, you can get a more specialist folivore ecology, like Endreids that really big lemurs have, or you can get a hard object specialist ecology like the Archaeolemurids show. So yeah, so access to defended plant resources really seems to be, to me, in my hypothesis, my model, to be a critical event in the expansion of lemur ecospace occupation. And this could be an adaptation to the forest expansion we see during the Oligocene. And if that's the case, I really don't think this is an adaptive radiation model exactly. It's more like a successive adaptation to new ecological opportunities as they occur on Madagascar, not a near simultaneous movement into new niches. Although it's possible lemurs get to Madagascar in the Oligocene, right? We have now maybe some evidence that might be occurring, which you can imagine might be something more like an adaptive radiation. It's kind of hard to distinguish without fossil record. So figuring out a little bit better the floral history of Madagascar, I think, will really be essential. So what are the actual histories of these plant communities? And there's work done on that, but I think that's probably the pathway to maybe begin to disentangle these possibilities. And one other product of this was a K-12 outreach lesson plan that I did and distributed through a program called Siren. So if anyone's interested, I need to put this on my website because I don't think Siren's still distributing it, but it's basically a lesson plan for North Carolina science standards, but it can be adapted that uses some scans that I made of these lemur teeth. And we're actually starting a Siren program here in Appalachia with Chris and David and a colleague at University of Pikeville, Rachel Messer. So look forward to that. And yeah, and thanks to everyone. And I definitely want to point out this was a collaborative work. So this is the main paper that came from it. So I already mentioned Shan. but also these other co-authors, some of them mathematicians, some of them evolutionary anthropologists that were definitely important. And that's coconut palm is that little animal there. He's a bush baby.
Wow. Well, thank you, Ethan. I have learned a tremendous amount about lemurs just from the get-go. 25% of primates, that's unbelievable. I had no idea it was that many on Madagascar. And looking at a fossil record and then making inferences on that fossil record in their diet, through mathematical equations, that's relatively new. That's not something we see a lot of happening out there. Have there been any studies like this where there is a good fossil record, and this has been done kind of blind to see if the hypothesized view of what these teeth might look like, for example, matches the actual fossil record? Or would that be something maybe you could do?
Yeah, that's a good idea. Because these continuous reconstructions of shape, I mean, it's been done with landmarks, but it's not been done with this approach.
Right.
And I don't think you could do landmarks on teeth because I think it would distort the teeth too much. So yeah, that's an interesting idea. You can think of some examples in primates even, because we have a really good Eocene fossil record for primates in North America. And I actually have all those scans, so I can probably try to do that.
I think we have several questions. Chris looks like he might have one, and then David, if you want to jump in after that.
Yeah, I mean, I was also just the dental tools that we have. I mean, I guess you're a paleo dentist, but they're fascinating, and they are things that have really only been possible with kind of new technology. And so I really, are there other groups that you've applied some of these dental tools to, or is kind of lemurs, because they are this really interesting, they provide some really interesting kind of test questions. Have we really focused on them more than some other groups to develop some of these tools?
Yeah, dental topography metrics and really the analysis of dietary adaptation in teeth generally, all the way back to sharing quotients, is always focused on primates. I think partly that's because primates present interesting questions. They're pretty diverse in their dietary ecology, but kind of subtle in their differences in tooth shape. But also I think because the people who developed them were just primate people in the primate world. And they got published in like American Journal of Physical Anthropology and journals like that. So there's definitely space. There was a recent paper on bear teeth that I actually reanalyzed some data from, and I'm working with Blaine to maybe add some bears to that. So that use these tools, use D&E and OPC and RFI. Trying to think of there's people have used them for weird stuff. Like someone used it to describe embryo shape. They used D&E to describe an developing embryo. But yeah, it's mostly been on primates and on primate relatives.
I think it'd be good for mastodons, as always. But anyway, yeah, it's really fascinating stuff. So yeah, so do we want to, David, do you want to tell the listeners out in Facebook land? Well, maybe we lost David.
No, I'm still here.
Okay.
Yeah. If you have questions, now's the time to submit them. Like I said before, leave a question in the Facebook comments on the video, or if you can't leave a comment on Facebook, I'm keeping an eye on the Twitter and Instagram Gray Fossil Site accounts. We do have a question from Charlie, who asks, are there any large fossil species of fossa that preyed on the larger fossil species of lemurs in prehistoric Madagascar?
So I should really have looked this up. I want to say yes. I think that's true, but I can't.
I think so too. I've heard of a large fossa. I don't know if it was like, I don't think this was like a tiger-sized animal, but bigger certainly.
Yeah. Who was the predator over time?
Yeah, I mean, fossa are the main predators of lemurs, terrestrial predators of lemurs now. Also, birds prey on them, and there are boas on Madagascar that prey on smaller lemurs.
Nice. And we've just got another question here from Mason, who says, what happened to the lemurs or the close lemur relatives on the mainland?
Well, we have no idea. They went extinct. Yeah, because there's no fossil record for lemur branch strepsirrhines other than maybe those eyes on mainland Africa or Asia. There's a suggestion there's an animal called bugti lemur that people thought was maybe a lemur from Pakistan, but it seems like it's not. So the other strepsirrhines, so we do have a fossil record for galagos and lorises. So some of those ones I mentioned and some more recent ones. So they just kind of hung out in Africa and Asia, and they're still around. And they've been about the same for most of their history. And then Adapiforms I kind of mentioned in passing. So this is big radiation of probably strepsirrhine primates that evolved mostly on northern continents, so in Europe and North America and Asia. And they all go extinct in North America and mostly in Asia, or mostly in Asia and in Europe at the Eocene to Oligocene transition, an event called the Grand Kapur, where global temperature gets colder and they can't live on northern continents anymore.
Well, it's interesting how bamboo eating drives a certain morphology, and would you say there's parallels to that dental morphology that you're seeing between the lemur, between the red panda, between the giant panda?
Well, they're definitely, yeah, they're crusty and robust. I think that's might be the way to put it.
Yeah.
I don't know about detailed. That'd be kind of interesting to see if they converge in detail. But there's a gestalt to their teeth because it is both. It is something that's both like a folivore will usually have teeth that are very crusty, but they don't need to resist hardness all that much. But these things are actually having to resist kind of hard foods too.
Interesting. So what's next for Ethan in terms of big ideas of research? You've got this tool that actually doesn't seem to be used a whole lot across non-primate groups. Is there a plan to maybe start using this tool on a lot of other groups?
Yeah, well, one thing I'm working on now is the data I collected on Eocene primates, so still primates, but I have scans for most genera of Eocene primate. There are a few I still need to get. And I want to look at their diversity through time. So there, instead of having to project back from extant animals, you actually have a continuous fossil record that shows the sort of increases and decreases of diversity, and see if if their diversity is related to climate events. Spoiler, I guess it doesn't seem to be. That's my SVP. So that's a project that I'm trying to get done. I am trying to work a little bit on bear teeth, as you know, Blaine.
Yes, definitely.
They're interesting because bears have maybe, I guess, some of the same character of primates in having these subtle dietary differences and teeth that are complex as opposed to some of the carnivore teeth. And then and also tooth wear is a big question that has been looked at in howling monkeys productively, and howling monkeys seem to actually increase the functionality of their teeth as they wear. So almost all these studies have been on unworn teeth, but of course most animals are walking around with worn teeth once they're past a certain age. And so finding systems to look at tooth wear is interesting to me. And so I've actually been looking at the tapers up at Great Fossil Site. So there's a good pitch for Great Fossil Site to maybe scan those. And it was, I guess, a couple of weeks ago, you had the Oreodonts on. I think Oreodonts are kind of cool to look at because they have like long continuous record and what's going on with because those are also teeth that wear. Those kind of selenodont teeth that get their functionality as they wear. So yeah, I think there's a lot of potential for applications of these tools.
We just got another question here, Ethan, in the comments from Tim, who says, fun question. What's your favorite haplorhine primate?
Oh, tarsiers, easy. That's my Facebook picture for a long time.
Well, you have to follow up with why. What is it that drives that?
Well, now we're getting to personality probably. I'm just always I'm drawn to kind of generalized animals that are, well, they're not generalized, they're very specialized, but animals that are outgroups, I guess, put it that way. So tarsiers are definitely the outgroup to the rest of haplorhines, and they resemble in some ways these fossil animals like oomamaias. So that's very interesting to me. They're very unique. They're the only faunivorous primate.
And what about the poor eye? I mean, it's so disgustingly cute.
I mean, those are great. They're great. I like small things too, I guess.
Yeah.
The eyes are great.
Here's
too.
a question from Bob, who asks, is tooth decay a factor in lemurs?
Yes, it is in one lemur. So in general, you know, humans eat this like ridiculous diet of sugar and acid all the time. And so we have all these tooth problems that like a normal mammal doesn't have. But lemur cata, the ringtail, eats this fruit called the tamarind. That is, it's an acidic fruit, but it's also in this really hard shell, and they just have to like crunch through it. It's kind of a unique thing about how lemurs eat. They can't really ingest with their front teeth because they have their tooth comb. So they have to ingest with their side teeth. So basically what they do is they pick these pods up and they just crunch them. And that seems to just wreak havoc with their teeth. They get all this tooth breakage and tooth wear that's really unusual for any kind of a wild animal. And there's an idea that maybe this is a disequilibrium, that they didn't used to do that this is something that's happened with humans displacing their populations into less agreeable climates and stuff like that. They've started to eat these tamarinds. So that's the biggest example of that kind of a thing.
Then I have a question that I've been wondering, as I've been watching through your presentation, you've got all these wonderful pictures of primates. You know, I think about someone like Blaine, whose specialties include things like bears and gators, and Blaine is lucky enough to live in a part of the world where you don't have to go very far to find bears and gators. But you're studying primates, which I imagine are very difficult to access in the wild, and especially, you know, in this continent where we don't have them. So do you just spend a ton of time at zoos? Do you find that you have to be more, if you want to learn more about primates or get more modern insight, do you find yourself having to collaborate with a lot of zoos or conservation institutions?
So none of my research has ever involved a living animal. So that's been less important from like and actually getting the work done perspective. But it's good to see them, right? To like get some idea of what they are like. And I happen to go to grad school at the Lemur Center of the Western Hemisphere. So the Duke University and the Duke Lemur Center has the most lemurs of anywhere outside of Madagascar. So you can see a lot of them there, and you know, they're in zoos. But yeah, it would be great. I've never been to Madagascar. That's I would love to go there and have a done dissertation on it. I know Jason Camelar, who's a famous lemur guy. I don't know if this has changed, but when I talked to him, he did a whole career studying different aspects of Madagascar and different aspects of lemur ecology and different areas of Madagascar. I've never been to Madagascar. So you can do it, but it would be great to see, especially to see the forests and to see what the animals are like in the forest, because I'm going to kind of have a vague idea of that.
Is this Lemur Center a place that we could visit?
It is. You have to schedule an appointment, and they go pretty far in advance, particularly right now because there's pent-up demand. But
okay. And how many species would one get to see, do you think?
Oh, I don't know actually top of my head how many they have.
Yeah,
I think
more
than
10. 20.
Yeah, I think it's like 20, something like that. And it's a bunch of lemurs, and it's also, they have bush babies, and they have, I think they still have a loris that's hanging on. They used to have more other non-lemur things, but they decided to focus on lemurs. Great place. And they have ii. They're one of the only places in the world to see an ii in captivity.
So we should take a field trip, Blaine.
Okay.
Get all the students together. Go see some
Paleo
lemurs.
Talks live with the lemurs.
Oh, that'll be our guest. Our guest will be a lemur.
Yeah.
And they also have so a lot of the specimens that I analyzed are from the Division of Fossil Primates that's at that institution, the Duke Lemur Center. So it's a very important paleontological institution too. A lot of subfossil lemurs, and also Egyptian Eocene things. Because there's a guy there named Ellen Simons who's worked for decades and decades in Egypt at the Fayum and collected a lot of important specimens, half of which are in Duke and half of which are in Egypt to the Cairo Geological Museum.
All right. Well, we're just about out of time. Is that right, David?
Looks like it.
All right. Well, thank you so much for teaching us about these lemurs and taking us to Madagascar today on this Friday, your birthday. Yeah, happy birthday again to you. And this has been just wonderful. And we'll see everybody again in 2 weeks for Paleo Talks. Thanks again, Ethan.
Thanks, Ethan.